Let's write some Lewis structures for polyatomic ions, and these are ions, which means these are not neutral anymore, which means that you may have excess of electrons or less number of electrons. Okay, so I'm just going to randomly pick 2 or 3 polyatomic ions and write the structure, okay, for those. So let's take something like carbonate ion, okay, CO3 2 minus. Now this is going to be a little bit different approach, and I'm going to start it in a more complicated way, and then we can take it a simple way as well. Okay, so the complicated way, or actually it's a better way of doing things, is what we call electronic bookkeeping. And electronic bookkeeping is when you take all your total electrons and then you keep subtracting as you're forming the number of bonds. Okay, so how do we do this? We have carbon over here, and carbon has 4 electrons, so you write that down, and then you have 3 oxygens over here, so each oxygen has 6 electrons. Okay, so 3 oxygen has 3 times 6 electrons, okay, in there. So which means we have a total of 4 for carbon, we have a total of 18 for oxygen, and then because this is an ion, you have a 2 minus. So because 2 minus, you also add 2 more electrons in there. Okay, so which means it has an excess of 2 electrons in there. So which means that you have a total of 24 electrons in this structure. Okay, so now what we're going to do is we're going to start very simplistically and then go ahead and make sure that we account for all the 24 electrons. Okay, again, between carbon and oxygen, what goes in the middle? Carbon goes in the middle. Why? Because it is on the left hand side of oxygen, okay, on the periodic table. That's all you have to do. So we place carbon in the middle, and then we go ahead and place the 3 oxygens around it, again as symmetrically as possible. You can write it down also, but this is how I wrote it. Okay, so the first thing you have to do is make sure that you have a single bond between all the atoms, because they're at least bonded with one bond. So each bond here takes care of 2 electrons each, which means that you have a total of 6 electrons. So 3 single bonds, and that is minus 6 electrons. Okay, that's what we did here. So now we are left with 18 electrons. Now we have to account for the 18 electrons. So we look at carbon. So technically speaking, carbon still has 1 more electron, right? Because carbon is supposed to have 4 electrons. So only 3 of them are bonded, which means that we can probably share 1 more electron with oxygen over here. Okay, because carbon has 4 electrons and it can hold up to 8 electrons. So now carbon has 4 bonds, so which means total of 8 electrons. Okay, so then 1 more bond on carbon, and that is again then minus 2 electrons, so which means that now we have 16 electrons to take care of. Okay, so now I'm going to go ahead and fill in some of the lone pairs. Carbon doesn't have any lone pair left because it had the 4 electrons and 4 of them are occupied. This oxygen is different than this oxygen and this oxygen. Why so? Because this one is double bonded, these ones are single bonded. So they're going to be different in the number of electrons that they have. So let's look at this oxygen first, because this is the one that is double bonded. All right. And so this oxygen, two electrons are here. They're bonded with carbon. So 1 electron here, 1 electron here, 2, 3, 4, 5, 6. Remember, that's the maximum number oxygen can have because it's in group number 6. So it has the 6 valence electrons, and then 2 electrons are being shared with carbon. So that's how it has the 8 electrons. Okay, hopefully you're okay now. So we have 6 electrons or 4 electrons that we assign to oxygen here. So 4 electrons on double bonded oxygen. Okay, so which means minus 4 over here. So now we have 12 electrons, okay, that we have left to assign. So this is electronic bookkeeping. Okay, as I'm making a new bond or I'm putting the lone pair of electrons, I'm also subtracting my electrons from here. So that way I know how many electrons are left. Now I said to you just a minute ago that these 2 oxygens are going to be similar. Why? Because they only have a single bond with carbon. So which means that these 2 oxygens are going to have equal number of electrons. Okay, so I have 12 electrons left. I'm just going to go ahead and divide it by 2, and that is 6 electrons. So now I'm going to assign 6 electrons to each of these oxygens. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that is all my electrons. I have accounted for all the electrons that I was given. I had 24 to begin with, and I have 0 left now. Okay, so let's write the structure again. Carbon, 1 oxygen here, and a double bonded oxygen here. 6 electrons, and only 2 pairs of electrons over here. And then you go ahead and put square brackets around it, and then you put 2 minus, okay, outside. This is how you would write for a polyatomic ion. Okay, this is the structure for it. Okay, let's write another one, and hopefully this would be good for you, because I'm going to take you to the next level now. Okay, and the next level is where you learn about the exceptions. Okay, and you've already covered exceptions by now. There are 3 exceptions to the octet rule. One is that you have less than the number of octet, which is anywhere from 6 electrons to maybe even 5 or something like that. So you have that. You have an expanded shell, and an expanded shell you can have more than 8 electrons, and then you have the unpaired electron. Okay, so those are possible. So I'm going to do sulfate now, and sulfur is below oxygen in the periodic table, and sulfur is one of those exceptions where you can have the expanded shell, and you are expected to know that. Okay, so that I said sulfur can have the expanded shell. That's why we can do this. Okay, I'm going to go ahead and do the electronic bookkeeping for sulfate also. So hopefully you can follow this a little bit faster. So sulfur is equal to 6 electrons. 4 times oxygen is going to be 6 times 4 is 24 electrons. Yeah, can you imagine? All right, I didn't know how to do that. And then 2 negative is going to be 2 electrons. Okay, there. So that's the total number of electrons I have, which is equal to 32 electrons. Okay, that's a lot of electrons to take care of. But you will see it will work out because we also have 4 oxygens, okay, to work with. All right, so let's go ahead and start with our structure. Sulfur goes in the middle. 4 bonds, oxygen, 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 oxygen. Okay, so start symmetrically with sulfur in the middle. And why are we writing sulfur in the middle? Because oxygen and sulfur are in the same group. So how do we decide that? If you have something left and right, then the left one goes in the middle. If you have something top and bottom, bottom goes in the middle. Okay, in general the rule is that the lower electronegativity element goes in the middle. Okay, so when you learn about electronegativity, that's what helps you decide, okay, what goes in the middle. Lower electronegativity element goes in the middle. Okay, so here I have 4 single bonds. 4 single bonds meaning I have 8 electrons. Okay, so 4 single bonds, which is minus 8 electrons. Okay, so that is going to be 24 electrons left. Okay, now sulfur has 6 electrons according to the periodic table, because sulfur is in group number 6, so it has 6 valence electrons, and sulfur is also capable of having expanded shell. This is something you have to remember. If you don't remember this, then you're going to get this question wrong. Okay, so sulfur has expanded shell. Why does it have expanded shell? And that you must have learned from the PowerPoint, that if something is in group in row number 3, okay, starting from sodium, then in row number 3, in shell number 3, you also have the d orbitals. Okay, and those d orbitals don't get filled until after the 4s. Okay, so those d orbitals are still available, they're just not filled. Okay, it's just like having a spare bedroom in the house which is just not filled. Okay, but it's there. Okay, so sulfur has an expanded shell, which means that the 2 electrons that it has, they can also form another bond. Now remember, oxygen cannot have an expanded shell. Oxygen is not capable. Okay, shell number 1, shell number 2, no. You have to have just the duet and the octet rule for those. Okay, and wherever possible, sulfur will have the octet rule. Okay, but this is one of those exceptions. So what did we do now? We added 1 more bond between sulfur and oxygen each. Okay, why did I do this? Because I know sulfur has 1, 2, 3, 4, 5, 6 electrons in the valence shell, and all 6 of them are bonded now. Okay, so now 2 bonds between sulfur and oxygen. So that means that is a total of 4 electrons. So which means now I have 20 electrons left. Okay, all right. Now just like we had for carbonate, okay, these 2 oxygens here with the double bond are going to be different from these 2 oxygens which have the single bond, okay, because these are double bonded oxygens. Generally speaking, if you have a double bonded oxygen, it means it's happy. Happy meaning it has the octet, okay, so which means that it's a very stable oxygen. Any oxygen that does not have the requisite number of bonds is going to have some extra electrons or less electrons in there. Okay, so how many electrons does oxygen have in the valence shell? 6 electrons. Okay, so I'm going to do for this electron first, and so oxygen is supposed to have 6 electrons in the valence shell. So 1, 2, which are bonded with sulfur, 3, 4, 5, 6. Okay, 6 electrons for this oxygen, and then again these 2 electrons which I used up already for bonding with sulfur. So 2, 3, 4, 5, 6 electrons. Okay, so here we are 6 electrons, and actually a total of 8 electrons that I just added, okay, to both of these oxygens, because 2 of each were already bonded. Okay, so 2 already were bonded, so I added a total of 8 electrons. So filled valence shell for double bonded oxygen. Okay, so which means 4 times 2, which is 8 electrons. Okay, so then minus 8 electrons, and now I'm remaining with 12 electrons. I hope this is going smooth for you. If you want to, you can rewind me and hear me again. Okay, so 8 electrons coming from the filled valence shell for the double bonded oxygen. Okay, and so I have to assign all the electrons. One way or another, I have to assign all electrons. So then I have these 2 oxygens left, okay, where these are with single bonds, which means that these 2 oxygens are going to be alike. If they are alike, that means I can take these 12 electrons, divide them by 2, and have 6 electrons each. So just like we did for carbonate, we are going to do here as well. So 6 electrons each that I'm going to assign to these oxygens. Okay, so those are the 6 electrons, and then 1 that it's sharing. Now, if you are thinking, how is it that I'm giving 6 electrons to this oxygen, but I gave only 4 electrons to this? Well, that is wrong. Okay, this oxygen also has the 6 electrons. Okay, but don't forget, this is a polyatomic ion. I actually have 2 extra electrons, which I have to place somewhere. So those 2 extra electrons actually have gone to these 2 oxygens. Okay, because technically oxygen should have only 6 electrons in the valence shell, but this oxygen has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay, so that is how we account for these extra electrons. So let's write the structure nicely and neatly. So we have sulfur, oxygen, 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 and then we have the double bond with the oxygen here, 2 lone pairs left on this oxygen, and then we have the 3 lone pairs on this oxygen, and then here is my final structure, okay, for sulfate. All right, I'm going to do one more for you in the next pencast, so if you still did not get it, then no problem, go ahead to the next pencast.